Okay, let's get started. We finished off with some ISA trade-offs in the previous lecture, so we're going to go deep into ISA today, and we're going to go even deeper into ISA in the next lecture. So hopefully it'll be fun. I have a lot of slides to cover, actually, so hopefully you're ready for a fast lecture. You can stop me by asking good questions. And I got the year right this time, which is good. Okay, that's the agenda. I already told you. There are some upcoming readings for next week and the week after so that you can start doing the readings. We'll talk about more ISA trade-offs next week, plus your lab and homework. There'll be a session on Wednesday on MIPS ISA tutorial and ISA trade-offs related to it. And it'd be good if you can do these two readings. Again, they're not. This is online, the LC3 ISA and the LC3B ISA. These are actually very good. This chapter is very good. As I mentioned, this book can give you a lot of insight. The week after, we'll talk about microarchitecture, basically how to implement the ISA. And we'll start with the very basic machines, single-cycle microarchitectures and microprogrammed microarchitectures. And then we'll go into pipelining, and we'll go into even deeper topics. Hopefully you'll understand everything. And this is good to read at that time. So keep this somewhere in the back of your minds while you're doing the readings for this week. And we've also provided some example critical reviews for you to see on the course website. They're on the course website, right? Okay, good. So you can take a look at them. There are 3 of them. And hopefully your reviews will be similar or better. Fortunately, they're not reviews for the papers you're reviewing. So you won't be biased by what has been written. Okay, last lecture recap very quickly. We've covered levels of transformation. We talked about algorithm, ISA, microarchitecture. So you all know what an algorithm is, what its 3 properties are, and whether you can eat carrots indefinitely or not. Right? Moore's law, and I recommended his paper. We talked about what is computer architecture. We defined it formally, or more or less formally. We talked about why study computer architecture, why it's exciting today, and why it's going to be more exciting going forward, in my opinion. We can talk about it again later when we get toward the end of the course. We started with some fundamental concepts, like von Neumann model. So you all know what the 2 key properties of the von Neumann model are, right? Who's brave enough to venture? Yes?
The program is stored just as the data, and it's sequential, strictly sequential.
Exactly. Stored program and sequential instruction processing. And we'll assume this model for the rest of this course, but that's not the only model of execution. There's a data flow model where an instruction gets fetched and executed only when its data is ready. So it's really data-driven. And we've talked about ISA versus microarchitecture, and we'll start with this in this lecture, and we'll go deeper into ISA. And your assignment, homework 0, is due today, and you'll keep on top of the assignments, hopefully. This was one slide we've covered. Basically, ISA, just as a reminder, it's the agreed-upon interface between the programmer and the hardware designer. It's the hardware-software interface. And microarchitecture is a specific implementation of it. It's not visible to the software. And we've covered this slide. I'm not going to go over it again. But basically, ISA is the book. And I'd recommend everyone to read this, I believe, increasingly growing book. It may be 1,000 pages right now, or 1,200. It's in 3 volumes. Actually, you'll learn a lot about architecture when reading this kind of books. I'm joking. It's not a required reading. But I'll give you some examples in this lecture and maybe in later lectures too. On the other hand, microarchitecture is a specific implementation of the ISA under specific design constraints and goals. And we'll talk about design constraints in a little bit. It's basically anything done in hardware without exposure to software. And again, this is specified by that book. You can actually expose anything to software, right? If you want. That may not be a good idea. You can expose all the control signals, and we'll get to that toward the middle of this lecture. Pipelining, for example, is usually not exposed in most ISAs today to the programmer. The programmer doesn't need to know how a pipeline operates internally, but that's a method to overlap the execution of instructions internally, and we'll cover that later. In order versus out-of-order instruction execution. Even though the programmer sees the von Neumann model, one instruction executed at a time before the next one is started, underneath, the microarchitecture can be out of order. can execute instructions in out of the program order and ensure that the programmer sees the specified ISA, the architectural interface. Memory access scheduling policy, one of the potential required readings, talks about this. That's not exposed to the programmer. Speculative execution, basically doing something before you know that it should be done. For example, preloading of the data. If you want to reduce the latency to memory, a lot of architectures today, a lot of microarchitectures today actually predict what location will be accessed later and preload that data into the cache. So that's not exposed to the programmer today. Actually, that could be, potentially. That's the prefetching part. Speculative execution is a more general term. Prefetching is an example of speculative execution. And there are many, many other examples. Superscalar processing, for example, fetching multiple instructions per cycle in a given cycle and decoding them, executing them. That's not exposed to the programmer. You could expose it to the programmer. Actually, there are some ISAs that expose this to the programmer. VLIW ISAs, for example, very long instruction word ISAs. This is in contrast to superscalar. You can actually fetch multiple instructions, and those multiple instructions may be required to be specified by the programmer. Programmer says, these are the 3 instructions that you can execute in parallel, and here I provide you a bundle of these 3 instructions, so execute them. And we'll talk about the VLIW model. Yes, you had a question?
Isn't prefetching exposed to the programmer at times?
That's right. So that's why there's a question mark over here. There are some instructions in the ISA that do prefetching, and we'll get to that.
But there is an offset in the thing. So
Well, there are specific instructions that says prefetch instructions. Yeah.
no,
Well,
there are also processors in general which have, like ARM has an 8-byte prefetch offset, right?
But that's not what he means by exposed to the...
Yeah, no.
I don't know what you mean by 8-byte prefetch offset. Maybe we can get to it when we talk about prefetching. But normally, load instructions are obviously exposed to the program. You can load data. But prefetch requires specific instructions, right? Such that the programmer can say, load this data to the cache. But I'm not going to use it in the registers yet. OK, there are many, many other things that may or may not be exposed. Caching, for example. Is it exposed to the programmer? Well, most of the time not, right? Programmer doesn't need to worry about it. But it may be. Like cache as a structure, the existence of a cache may be exposed to the programmer, right? With the prefetch instructions, for example. We'll get to that. OK, there's voltage frequency scaling. That is actually exposed to programmers, right? System software programmer needs to do that. But that may not. That doesn't have to be. Microarchitecture can do it on its own, right? The hardware can say, oh, this core is right now idle, so I'm going to reduce the frequency of it, right? Or mostly idle, so I'm going to reduce the frequency of it. That's an example of voltage and frequency scaling not being exposed to the programmer. There are no instructions that can change your voltage and frequency, but the hardware does it automatically. But if there are instructions, then it's part of the ISA, not microarchitecture. So a good way of thinking about it is, are there instructions that operate on the structure or on this particular thing? If so, then that's part of the ISA, right? That's part of the architecture. If not, then it's not part of the architecture. Pipelining, for example, that's not part of the architecture. And you cannot modify pipeline registers with instructions. Instructions flow through the pipeline registers, but there are no specific instructions to modify the pipeline registers. OK, think about these as we go through examples. Let me give you one example. Property of ISA versus microarchitecture. And we'll take the example of an add first. Is an add instructions opcode, is that a property of the ISA or microarchitecture? ISA, right? Clearly, opcode. Someone needs to compile to that opcode. Number of general purpose registers. Say it again?
Programmer has an idea of...
Microarchitecture? It depends. Well, I will argue that this is part of the ISA, right? Because assuming there are instructions that operate on general purpose registers, and usually when we say general purpose registers, it's really exposed to the programmer, exposed to the ISA. That's really part of the ISA. Instructions take registers, general purpose registers, as operands, right? Add, for example, add R1, R2, write the result into R3, which means that that's part of the ISA. Number of ports to the register file. Now that's microarchitecture probably, right? Usually there is no instruction. In an instruction, you don't specify which ports. that the instruction uses, right? That's part of the hardware. Underneath, you can have maybe only one port to the register file and access the register file twice to get 2 operands. Okay? Number of cycles to execute the multiply instruction. Again, yes, this is part of the microarchitecture. Again, this doesn't have to be, right? In some architectures in the past, VLIW architectures, for example, that was exposed to the programmer such that the programmer can do good scheduling of instructions. You can reorder the instructions such that you can overlap latencies of instructions, and we'll get to that. Whether or not the machine employs pipeline instruction execution, we already talked about that, right? Pipelining is usually not exposed. But basically in today's machines, pipelining is not exposed. Most of today's machines. And again, as an architect, you can imagine machines that are very different. Okay, we've already talked about this, but microarchitecture is an implementation of the ISA under specific design constraints and goals. As a result, there are many, many microarchitectures. And the microarchitecture is really determined by the design point itself. The design point is the set of design considerations and their importance. And this leads to trade-offs in both ISA and microarchitecture, by the way. And there are many considerations, and the reading that you're doing, the LPAT reading actually talks about a lot of these. And hopefully you'll write a review on it. But cost is one of the big drivers, right? Remember we talked about the adder implementation before. Do you do a bit serial adder with just one full adder, or do you implement a carry lookahead adder? Well, that has implications on maybe all of these, right? Cost certainly, but bit serial adder is much less costly, but it's lower performance, and by itself it doesn't consume a lot of power, right? Because at any given time you're adding 1 bit, not 32 bits. Energy consumption, it probably affects your battery life somehow, but that's a different trade-off because now your program takes longer to execute, but you're consuming less power at any given point in time. So it's not clear how the energy works. That's why you need to evaluate it and think about it and model it. Well, these are maybe different with the adder, so I'm not going to go into these with the adder. But availability is a constraint also. For how long should your system be able to run, right? In data centers, for example, in critical server workloads, you want very high availability. Reliability and correctness. So these are important also. Sometimes, and your design point, and also time to market. And your design point determines all of these. And what is design point in turn determined by? It's really determined by your goal, right? What is the problem that you're trying to solve by building this machine, building this platform? Which means that what are the applications you're targeting? It could be a general purpose machine. You can say, I'm going to execute any application that anyone in the world can write at any time, right? That's the idea of general purpose design. That's your intended users or market. Or you can say, I'm just going to execute matrix multiplication, right? Really, really well. That's a more application-specific design. And the trade-offs that you make will be determined very, very differently. Does that make sense? And we're not going to go into these in detail right now, but it's also good to think about, in some cases, maybe you give up some of these, right? Maybe sometimes you give up performance to minimize cost. Sometimes you give up performance to minimize power consumption or energy consumption. Sometimes you give up reliability to actually improve your performance, right? Does that make sense? That could be interesting, right? Or improve your cost. Maybe you can say, I don't care about these errors that happen in memory. I just want to because my data is very error tolerant, right? If your application is spaced that way, you can make different trade-offs across these considerations. So this is really critical as an architect because that leads to all of your trade-offs. That determines all of your trade-offs. That's why most of the answers are not set in stone. Most of the answers to the questions we ask are really it depends, right? And usually it depends on the workload is a good answer. But I'm not going to take that answer for all of your answers in the questions on the exams. But usually you need to qualify your answer, right? It depends, but it depends on what? Okay. So application space is really important, and this is really what drives a lot of the architectures also. And this is a paragraph from the paper that you're reading. And there are many, many applications. And as long as people keep dreaming, they will come. So at some point, we'll talk about in-order versus out-of-order execution. At some point, somebody said This was, I think, in the early 1980s. There was MIPS R2000. It's a machine that's really, really simple. And somebody said, why do we want anything better than MIPS R2000? Anything higher performance than MIPS R2000? MIPS R2000 was in order. Ideally, maybe even less than 5-stage pipeline. It could be 3-stage pipeline. Well, this is the reason why anyone wants something higher performance than MIPS R2000, because you want to enable new applications, right? It's a chicken and the egg problem. If you don't produce a higher performance machine, probably people will not build applications that can execute, can do more, right? But if you build the machine, applications will appear. Okay, so trade-offs are really the soul of computer architecture, or soul of engineering in general, but we're going to cover those in the context of computer architecture in this course. And there are three kinds of trade-offs that we will cover. We'll start with the ISA level trade-offs in this lecture, and then we'll do a lot of microarchitecture level trade-offs, and these are interrelated. And also system and task level trade-offs, how to divide the labor between the hardware and software. And computer architecture is, another definition is, it is the science and art of making the appropriate trade-offs to meet a design point. Right? You can make many trade-offs to meet the same design point, but eventually what you design could be different. Okay, why art? I think we've already covered this, right? It's art because we do not really fully know the future, applications, users, and market. You're really designing for the future. Right? You may know the current applications, but if you want your architecture to live, you really are designing for the future. And a lot of things change. There are new demands from the top, so you need to look up. New issues and capabilities at the bottom. I've already given you this slide, so I'm going to go through this really quickly. There are new demands and personalities of users, and all of these change. So it's really hard for you to make this an exact science. And if you make this an exact science, you should really win 10 Turing Awards, probably. Because if you want to make this an exact science, you need to be able to model what's going to happen into the future, right? In the applications, in the users, in the technology, and say that, okay, this is the design that I'm going to choose, given all of this, right? Does that make sense? It's a little bit different from, maybe that's not the perfect analogy, but in my view, it's a little bit different from building a bridge, for example. A bridge, hopefully, you kind of can guess the future is relatively constant. You know what's going to go on top of it. Well, even that may change, right? Somebody may design something that's huge that goes on top of your bridge. In a sense, you can apply principles and model things, assuming that the future is more or less constant, and you're going to have the same application running on that bridge, which is car traffic, I guess, or truck traffic. Or you can design for the worst case. If you have so many trucks, then this is what's going to happen. If you have the worst wind, this is what's going to happen, and this is the design of the bridge. Whereas it's a little bit different in the architecture case, because you really don't know what are the applications that people are going to run in 10 years. And the future is also not constant, because the demands change, technology changes, and users also change. I'll give you one analog from macro architecture, and then we'll go into trade-offs. I like giving out analogs from macro architecture. So future is also not constant macro architecture, right? Because buildings always get used in different ways. Can anyone answer this question? Can a power plant boiler room be later used as a classroom? Hammerschlag hall, someone says. And they're right. That's true, actually. So this thing that we're in today was a boiler room at some point only. And it was like this. This is a picture from, I believe, 1970s. And at some point, at the west end of campus was a small structure that housed the boiler room that functioned as a school's power plant. Below, in the rain beside the railroad tracks, a farmer's goat grazed. Anyway, you can, I guess, make it more literary. And occasionally wandered up to eat the grass of this yet untamed end of campus. At some point, machinery hall was built on top of that boiler room. And the massive tower, which has become a symbol of Carnegie Mellon, was designed to disguise the smokestack. And architect, who's an artist also, Hornbostel, created a temple of technology that would become one of the most renowned buildings of the Beaux-Arts style in the country. This is actually taken from the picture right next door. I guess my camera was not very good. And early course catalogs described the boiler room as a classroom where students learned about power-generating machinery. It's appropriate, I guess, right? The tower continued to belch smoke until 1975, but in 1979, the boiler room became the cleanest room on campus with the construction of the nanofabrication facility. Right. Sounds good. So future is not constant here also. But the good thing is, I guess, you can add stuff in macro architecture, whereas once you build a chip, you may not be able to add stuff. Although, it's always good to think about that, right? How can you adapt to the future? And this is part of the task of a computer architect. You have many options in adapting to or maybe predicting the future. You may have a lot of bag of tricks. One is keen insight and good design, certainly, which hopefully you will learn at the end of this course by looking at these different trade-offs, right? By looking at a problem and a solution, if you can say these are the trade-offs, upsides and downsides, given these constraints, that's how you develop the keen insight and good design. But also good use of fundamentals and principles. For example, you can use some other principle like reconfigurability to adapt to the future, right? Maybe you add some amount of reconfigurable logic attached to your general purpose processor design such that you can adapt to the future workloads a little bit more. Or maybe heterogeneity. These are things that we will discuss. You don't have a single homogeneous design, maybe not a single DRAM type memory, but also some other types of memories, right, that are optimized for different purposes. And then allocate your data across those memories. So these are design principles that can apply to any parts of the platform design. And we'll cover some of these, so you don't need to know all of these yet. And good use of underlying technology also is important when you want to adapt to the future. Because if you use a technology, let's say, that's going to be obsolete in 2 years, and somebody will come up with a technology that's much faster, well, then you have a problem, right? You've designed all of these complicated algorithms in the hardware, made your design much more complex, and to overcome the downsides of some technology. It could be DRAM technology. Let's take DRAM, right? Let's say it's unreliable. It becomes increasingly unreliable going forward. So you design all of these memory controller features to overcome those reliability issues like we discussed, the disturbance errors. Your design becomes complex. But 2 years later, someone comes up with a technology that's much better than DRAM and doesn't have all those issues. And someone designs a machine that's much cleaner, much faster, much more efficient. Well, you're out of the market now. Right? That's why looking into the future and good use of the underlying technology is important. Any questions? No. OK. So now we can do the deep dive into ISA principles and trade-offs. This slide is definitely not comprehensive. And there have been many, many different ISAs over decades, few of which have survived, I guess fortunately or unfortunately. But x86 is one of the dominant ISAs today. But there have been many, many ISAs. I'm going to give you examples over some of these. And you don't need to know all of these. This is just to give you that the space of ISAs have also been rich. Microarchitectures have been richer, of course, because of what we discussed, right? The interface, you cannot change the interface as fast because that's affecting all the software. And that's actually part of the reason why only few ISAs have been very successful today, right? x86 has been successful. There are some other ISAs over here. ARM has been successful. There are other ISAs that have been successful in specialized domains, and I'll give you examples of that. But PDP, Program Data Processor, that was Digital Equipment Corporation's early ISA. It turned into VAX, Virtual Address Extensions, which was the x86 of the day in the 1970s and 1980s. And then it turned into Alpha, which is the extension of that. So that's the progression of that ISA. And then Alpha died after Digital Equipment went belly up. Digital Equipment Corporation went belly up. There are other ISAs that I'll give you examples of. But not all ISAs are the same. There are some ISAs that are VLIW, which we will talk about. Basically, you can actually have multiple instructions as a bundle, and the programmer specifies that. And there are some other ISAs that have SIMD that are much more data parallel. So what are the fundamental differences between these ISAs? Basically, there are lots of them, actually. Yes?
Doesn't our PC count as a RISC ISA?
Well, that's a good question, actually. Initially, it was RISC, but it's so if you look at power, now I have to remember the exact acronym, but the last part is really extended RISC. Initially, when IBM came up with power, it was Power 1, and these two stood for extended RISC. I don't remember what the POW stood for. Can anybody look it up? Anyway, you can look it up later. But it's really risky, but it has some features that are complex. We'll talk about RISC versus CISC. RISC means reduced instruction set computer, if you haven't heard about it. So we'll talk about it in this lecture. And the key distinguishing features of RISC are it's really simple instructions. But PowerPC has some complex instructions. That's why I didn't classify it over here. OK. So how complex are the instructions, for example, is one difference between these ISAs. VAX happens to be one of the most complicated ISAs. And I'll give you examples from that. But the basic element of the hardware-software interface is the instruction. It consists of two things, basically. Opcode, which specifies what to do, or what the instruction does, and the operands, which specifies who to do it to, right? Basically, the operand values. So this is one example from the alpha ISA. If alpha wasn't a dead ISA, I would be teaching using the alpha ISA. You're fortunate. It's kind of unfortunate that it's a dead ISA today. There are no compilers for it, whereas there are compilers for MIPS, for example. Well, there are compilers for alpha from 20 years ago, but you don't want to use them. And there are cross-compilers, too. It's a beautiful ISA, in my opinion. If you look at it, it's kind of nice. And we'll talk about some of these properties. So opcode is always in the same place. That property, or a particular field, is always in the same place in an instruction. That particular property of an ISA is the uniform decode property. Make sense? You're uniformly decoding. It's fixed length, if you look at this, right? An instruction, regardless of whatever instruction it is always 32 bits, 4 bytes. But that's not all ISAs make this choice. Some ISAs are variable length. Some ISAs are non-uniform decode. Sometimes the opcode is here, sometimes the opcode is here. Well, it makes the hardware a little bit more complex, right? So we're going to look at some of these trade-offs. In this case, the operands are here. For example, for the operate instructions, operands are specified. There are 2 source operands and 1 destination operand, and this is the function. MIPS looks like this, and you're going to get really familiar with it, maybe more than you would like, by implementing lots of different execution engines for MIPS. So it's kind of similar to alpha in a sense, right? In this case, there are 4 different formats. In this case, there are 3 different formats. ARM, well, it looks a little bit ugly, but it's kind of still kind of regular, right? If you look at it, condition codes are always here. Opcode, kind of here. Registers are always here. So it's more like a RISC architecture, but it's a little bit more complex too. So basically, an ISA really specifies a set of instructions, their encoding, and the specification of how they operate. So this is the LC3B ISA. It's an instructional ISA. And maybe I'll open it so that we can look it up a little bit. I'll give you some examples from it. It's called the Little Computer 3B. And this is its ISA manual. It's nice because it's only how many pages? 25 pages, as opposed to 1,200 pages of x86, right? That's why I'm going to give you examples from this. But I'm going to give you examples from other things also. So if you look at this ISA, this is really the manual. This is really a summary of which instructions exist and what is their encoding. And I'll give you some examples that the ISA designer, some choice the ISA designer can make. So if you look at it, there are 2 instructions that are here, 2 encodings that are not used. Right? These are unused instructions. Why would you want to have unused instructions? Yes?
If you decide that there's something underneath in the microarchitecture that you can exploit, you can add a new instruction if you wanted to.
That's right. In the future, if you want to expand the ISA, now you can expand the ISA, right? By leaving some room for the future. Because the hope is that over time, this ISA will live maybe decades. And 5 years later, there may be some important applications that want some other instruction, right? And you decide to add those instructions. So this is important when you're designing an ISA, having some flexibility. It provides you flexibility to add more instructions because the future is not, again, constant, right? It's very difficult to come up with a set of instructions that can execute everything. And this has happened many, many times over decades. We'll see, for example, in the x86 architecture, people have added MMX instructions, multimedia extensions, right, that have appeared in the 1990s, 1995 or so. Well, that was added because imaging, videos, they become very popular, right? And if you actually can have instructions that can specify one operation that can operate on multiple pieces of data, you can do a lot more work. And that's what multimedia extensions did, actually. They're really SIMD instructions, single instruction, multiple data instructions. And they were added to the ISA because ISA had the flexibility to consume them. If your ISA, if you had already set your ISA in stone such that nothing could be extended, well, that's a bad idea. Never do that. Okay, there are some other things that are interesting here. Obviously, I cannot talk about everything, but there is a concept of bit steering. Does anyone know what that is? Basically, a bit in the instruction determines how the later bits are interpreted. Well, opcode is a really good example of that, right? Opcode tells you how you should really interpret the other bits. Because, for example, if you look at 0001, that's the opcode. That basically tells you the rest of the bits should be interpreted as DR, SR1, an operation specification. Whereas if your opcode is, let's see, 1000, the rest of the bits kind of don't matter, right? But there is also another example over here. Maybe, well, I'll give you from alpha, sure. Well, maybe I'll give you over here. This is also nice. So alpha is also nice. Let's see. Let's look at the add over here. Can you guys see this? Probably not. Is this first of all turned on? Light. That's a good. Now this is the real test. Okay, there you go. Oh, no. Okay, document camera. Wow, it worked. It's not exactly where I wanted it, but I'm not going to touch it. And if we zoom, there you go. This is basically add instruction definition specification from the LC3B ISA, and this is online. You can look at it. But basically, there are two formats of add instruction. This is the assembler format. The source register, one is always a source. And the second operand, the first operand is always coming from a source register. The second operand can be a source register, a general purpose register, or an immediate value in the instruction. And this is the encoding for the top one, where you have two source registers, and for the bottom one, where you have one source register and one immediate value. So if you look at this, how do you distinguish between these two? How do you decide, how does the hardware decide whether or not the second operand is a source register or an immediate? Well, it's this bit 5, that makes the difference, right? If you look at it, the operations in pseudocode says if bit 5 is 0, then the second second operand is a source register. Otherwise, the second operand is a sign extended value of this immediate. So this is really the steering bit. It's really steering how the hardware interprets the rest of the bits over here. Make sense? Basically a mux, right, in the end. Well, not exactly a mux. It determines your control signals because now you need to access the register file. So that's the concept of the steering bit. Well, the steering bit gives you a lot more power in the instruction, right? Now you can have different operands, in a sense. But it also makes the decoding a little bit more complex because now the interpretation of what's coming next depends on the interpretation of a previous bit in the instruction, right? So we'll get to that, actually. Okay, well, the other examples over here. Okay, I guess they're symmetric. That's good, at least. This is another example. This is very similar. Bit 12, if bit 12 of the instruction is 0, the RB field specifies a source register operand in alpha. And this is, in general, operate instruction. It's not only add. If bit 12 of the instruction is 1, an 8-bit 0 extended literal constant is formed by bits 20 through 13 of the instruction, which is right here, instead of here, over here. The literal is interpreted as a positive integer between 0 and 255, and 0 extended to 64 bits. Okay, you can read the rest in that document. But here, the designers have made a choice, right? Here, this immediate is sign extended, whereas here, it's 0 extended. Well, even that's a choice. You've got to make these low-level choices whenever you're designing an ISA. Why would you want to sign extend versus 0 extend? Well, if you want to operate with negative values easily, probably sign extending is a good idea, right? Whereas here, you need to do something else to actually turn this into a negative value, right? So you need more instructions to actually operate on a negative literal over here. So these choices determine whatever comes up above you, right? The compiler, for example. How does the compiler incorporate a negative immediate in alpha versus in LC3B? You can think about it. Okay. I'm not going to change the document camera. Is that okay? Can you guys follow it still? Maybe I'll turn off the document camera to make life easier. Ooh. What is that? I just pressed. I think there are some errors that are happening here. If I press light, all right, I'm not going to touch it. I don't like the smell of burning rubber, though. Okay. Well, I kind of don't like this actually, so let's do it. Okay. So we've talked about some elements of the ISA, which is the instruction. But instruction sequencing model is also an element of the ISA. ISA determines your sequencing model, control flow versus data flow. And we've discussed some of the trade-offs. And you can think of many, many more trade-offs. Instruction processing style. And a homework question deals with that. What do I mean by processing style? This specifies the number of operands an instruction operates on and how it does so. So there have been many machines. There's 0 address machines, 1 address machines, 2 address machines, 3 address machines. Have you guys been familiar with this in any course? Well, you'll get familiar with it when you do the homework question. A 0 address machine is, for example, a stack machine. What does it mean? Basically, it means that an operate instruction takes 0 operands. You just say add. Can you imagine how this happens? Well, the operands are implicit in the instruction, actually. In a stack machine, basically, add the top 2 values in the stack. Always. Because you never specify where the operands are. But you of course, load and store or push and pop into the stack. And you'll get this good exercise, hopefully. Accumulator machine, an operand takes, an operate instruction takes only 1 operand, and that's the accumulator. And we'll take a look at that also in your thing. I'm not going to go into these details because you're going to an example in your homework. But 2 operand machine, you have 1 source, 1 destination. Right? Let's say you do an add of 2 values. It's really your source plus destination, and the result goes into the destination. Right? 3 address machine, 3 operand machine, you have 2 sources and 1 destination. So this is kind of nice because destination equals source 1 plus source 2. Now you can specify it nicely. Okay? In the stack machine, I'll give you an example in a little bit. What happens is you take the top 2 values of the stack, add them. When you do an operate instruction, let's say add, it takes the top 2 values on top of the stack, adds them, and places the result on the top of the stack. So the locations are always implicit. And a lot of calculators were built using the stack machines. Later they moved to accumulators to have more flexibility in the calculators. And then later people have moved to 2 operand machines. So there are many trade-offs related to this, actually. I'll cover a couple of these. So if you have a 3 address machine, now you need to specify the operands, right? Your instructions are bigger now. Whereas if you have a 0 address machine, your instructions are much smaller. But maybe you execute more instructions. Right? You get much more compact code size with a 0 address machine. Because, again, you're not specifying the location of the operations, right? But your execution time may not be faster. And maybe you don't have a lot of flexibility, right? So one example, let me give you the example of the stack machine. You get small instruction size because no operands needed for operate instructions. As a result, you get simpler logic and compact code. Right? You get efficient procedure calls. That's one other benefit of this, because you can have all your parameters on the stack. Have you guys seen the? You guys know C, right? C has an activation stack, right? And it does parameter passing by passing parameters to the functions. Well, in a stack machine, this is really easy, right? If you have a stack, if everything operates on a stack by pushing let's say you keep pushing values on a stack, your parameters are already on the stack, right? There's no reason to copy those parameters into registers such that a later function actually uses them. You'll understand this more once you do some of the exercise, although we don't talk about this parameter calling. So if you're interested, you can dig more. The downside of a stack machine, or a machine basically that has only 0 operands, that cannot specify any operands, is really now you're limited by expressibility, right? You cannot express computations that easily, or you cannot map computations that easily on this machine. Well, computations that use postfix notation are easy to map. Do you guys know postfix notation? Well, a stack works nice if you have the last in, first out behavior. Right? I guess I need a pen here also. And I'll need to make this work again. Let's do right display this time, maybe. I'm really testing it now. Okay, good. So for example, let's say you have 5. Can you guys see it? Okay, good. 5 plus 7 times 8 times 9. It's kind of nice, right? You can do it in postfix notation. But if you want to calculate this, let's say this is your result. This is nice to. This is easy to do on a stack machine, right? How do you do it? What do you push first? Somebody said push 9. Yeah, you push 9, right? Because that's the last thing you're going to. That's the last computation you're going to do. Okay? So you push 9 on the stack. And so now your top of stack is this, 9. And then you push 8 on the stack, right? And then you push, I guess, either 5 or 7 on the stack. Let's say 5. And then 7. Is that right? Okay. And then you do an add. What this add does is it takes the top 2 values of the stack. You always have a top of stack pointer. And then does the addition, replace it with the top of the stack.
Why does it do the replacement thing? I mean, it shouldn't it just, unless you pop those values which you pushed.
Add is an implicit pop on.
Yeah, that's right. Add. That really depends on the specification of the instruction. Yes. So if the specification is such that add does an implicit pop,
Yeah,
which are actually very good that you mentioned, because I didn't tell you that it does an implicit pop. It does an implicit pop in this case, but it doesn't have to. Again, you're an architect, right? You can design a machine that doesn't do that implicit pop. But the beauty of this is it's very efficient, right? If it does an implicit pop, now you can map this computation really efficiently on this machine, right? If all you're doing is designing a calculator, then maybe doing an implicit pop is a good idea. And a lot of the old calculators actually operated using this postfix notation, right? Okay, you do an add, you get the rest, right? And then you do a multiply, which does basically this. And then you do another multiply, and you have the result, 96 times 9, at the top of the stack. Now you can do that pop. You can pop it to an address that takes this 96 times 9 and puts it into somewhere in memory. Make sense? Yeah?
There's no saying here that every instruction takes equal number of cycles, right?
No, there's nothing that's specified. This is the ISA. This is the ISA interface. Okay. But if you cannot express your computation this way, then you have a problem, right? Okay. Now you see. And maybe you cannot perform operations on many values at the same time, right? Because you're really operating only on the top n values. Maybe you can expand the operation such that you can operate on top 10 values. You can define a polynomial, for example, but that starts becoming more complex. So as a result, these machines are really not flexible. That's why people have started designing machines that are 1 address, 2 address, and 3 address later on. So this is one but the upside, you give up flexibility, but now your hardware is really efficient. This is really an example stack machine. It's really simple if you look at it. You have one ALU, and you just need the top of stack over here. You don't even have to buffer it, right? You have the data stack over here, and you keep operating. The one value comes from the top of stack, and the other value comes from the second location in the stack. This is just a high-level example again. Yes?
What is the return stack for?
So that's actually to do procedure calls, function calls. That's the return address stack. We'll get to that also. Existing machines are return stack also. Man, we're not gonna. Don't worry about it. But if you're interested in it, you can go and talk with Phil Koopman, who's sitting in the A level. He's actually designed a lot of stack machines when he was a computer architect 30 years ago or so. He's a professor here right now. And actually, this is it's kind of a cool book that he wrote in the late 1980s, which you can get and read about. I think all of it is online, actually, on his website. So this is the same example, well, a similar example. You push two values, and then you push, and then you do add plus, add and multiply. Okay, there are other examples. Not all machines are stack machines, fortunately. Life is easier. PDP-11, for example, is a 2-address machine. It had an add instruction with a 4-bit opcode and 2 6-bit operand specifiers. Well, why was it a 2-address machine? Because they wanted 16-bit instructions, and they wanted 64 registers. As a result, that's how they decided to have a 2-address machine. Because you cannot have 16-bit instructions and also three operands that are 3 operands out of the 64 registers, right? Okay. So this advantage of 2-address machines, which you will also see in your homework, is one source operand is always clobbered with the result of the instruction. Because what this does is you take the source operand and you operate on destination and write the result on the destination, right? Which means that whatever value you had in destination before now gets clobbered with the result. Well, what if you needed that value, right? How do you ensure that you preserve the old value of the source? Maybe you use it for some other operation also.
You need to maintain copies.
That's right. You have to copy it somewhere else, right? Which means that you need to move it somewhere else. So you do a lot of moves or copies before you do this. Okay. Some other examples. x86 is a 2-address machine. Alpha is a 3-address machine. What about MIPS? I've already shown you examples, right? 3-address machine, right? Yes, it is a 3-address machine. It had register 1, or RT, RS, and R something. ARM is also a 3-address machine. But one of the most popular ISAs is not a 3-address machine, as you can see. And there's also the notion of memory-to-memory or load-store machine that we will talk about also in a few slides. So basically, instructions are definitely the elements of an ISA. We talk about the address machines, but how do you obtain the operand is part of the ISA also. This is called the addressing mode. Basically, the mechanisms that you have to obtain the operands. And there are many different addressing modes. Can you guys guess why? Again, to accommodate the different ways of accessing data and programs at the high level. And we'll see a lot of examples of this, especially later. Hopefully, we will get to it today. But I'll get to this. But before we go into addressing modes, data types are also very important. What is a data type? Have you guys seen it? You must have seen it in 213. No? Basically, it's a representation of information for which there are instructions in the ISA that operate on that representation, right? Integer is one data type. Floating point is another data type. Character, binary, decimal. These could all be data types, right? You can have a data type decimal. Yes?
Are addressing modes just a form of bit steering? Like, because...
So, well, bit steering enables 2 different addressing modes. That's a good question. So in the previous, we'll get to addressing modes in more detail. That's why I skipped it. But in the previous example of add, you had 2 different ways of obtaining the second source operand, right? It could be immediate. It could be another register. Now your addressing mode is immediate addressing mode and register addressing mode. There are 2 different addressing modes. And the way you decide, you pick which addressing mode is used, is that bit that's steering you. Make sense? Okay. Let's cover the data types first, because this also affects the complexity of the ISA. So a lot of ISAs actually have integer and floating point. But again, that's a design choice, right? You don't have to have floating point data type in your ISA. You don't have to have floating point operations. In fact, many early reduced instruction set computers didn't have floating point operations. They said, we're going to do only integer data types. Is that a good idea? Well, again, it depends, right? if the only thing you want to execute is integer operations, maybe that's a good choice. But it turns out in the world there are people who want to execute floating point operations. And if you want to design general purpose ISA, looking into the future, you might want to put floating point operations. And that's exactly what a lot of the RISC ISAs, all of the RISC ISAs did. MIPS, for example, didn't even have a multiply operation. Well, but we're talking about data types. We'll get to that. Basically, it didn't have floating point, but now it has floating point. So there, you can again dream over here, right, and have many, many more data types. You can have doubly linked lists, for example, as a data type in the ISA. You can have instructions. You can have queues, strings, bit vectors, stack. VAX ISA, for example, had insert queue and remove queue instructions on a doubly linked list or a queue. So your data type is now a queue or doubly linked list. And we'll get to this again. x86 has complex instructions. Again, in your homework, you will see these data types. You have an opcode scan that operates on character strings. And you can actually have many other instructions that operate on character strings. So string is a data type now. It's not just a character, but also a string. Push pop, so x86 has stack as the data type. x86 has a lot of support for stack operations for procedure calling, actually. Again, this leads to a lot of trade-offs. I guess one question. What is the benefit of having more or high-level data types in the ISA? Can anybody guess?
Smaller code.
It could be smaller code, that's right. Yes?
Easier compiler optimization.
That's right. It could be easier compiler optimization. Basically, compilation is easier now because you're very closer to the compiler. But what is the disadvantage? Complexity, right? It could be complexity. It could be more work on the programmer, more work on the hardware designer. Okay. Again, the trade-off is between the programmer and the microarchitect, right? You're making microarchitect's life harder by adding more and more data types, but you may be making the programmer's life easier in this case, because the programmer now doesn't need to, or compiler doesn't need to map a doubly linked list into small operations on integers and pointers. Instead, you say, add to the list. Let's say you have an instruction like that. We made it up. But you could. There's no reason why you cannot. Right? So you're making the programmer's life easier in this case. So this will bring us to the concept of semantic gap, which I will talk about a little bit later. Data types are really coupled tightly to the semantic level or the complexity of instructions. What is the semantic level? Semantic level means how close are the instructions to the constructs in the program, right? If the instructions are really close, meaning that, for example, they specify operations on doubly linked list, the semantic level of the instructions are really high, right? Which means that the semantic gap is low. So maybe I'll draw this right now, and we'll cover this in more detail later today. I guess do the right display. So you have a high-level language over here, or program, let's say. And then you have, at the bottom, control signals. And you cannot see it. There you go. Now you have it. And semantic level of instructions can be here if you have very few data types, or your data types are not close to the language. Or the semantic level of the instructions can be here if you have data types that are exactly what you have in the programming language or the programs that you write. And this distance is really the semantic gap, how close you place the ISA or instructions and the data types to the high-level language. Again, we'll get back to this. There are a lot of trade-offs. You can place the ISA over here, or you can place the ISA at the control signal level, as we discussed, at the high level, or you can place the ISA at the high-level language level. And that's a very different trade-off that you're making right now. Okay. So think about it for now, but we'll cover it in more detail. So an example is early RISC architectures versus, I like contrasting them. Early RISC architectures, MIPS, for example, was an early RISC architecture. And they made the choice that only integers would be the data type. And Intel 432 was one of the more complicated architectures. It had data types, objects as data types. How many of you program with object-oriented languages? A lot, that's good. So if you had some objects or classes as part of your data structure that are implemented in hardware, and you can expose them to the programmer, maybe it's a lot easier for the compiler to take advantage of that if you're compiling from an object-oriented language to hardware. Right? So think about this. One example, I'll finish the data type discussion with the BCD. How many of you have used BCD, binary coded decimal? Yes? Oh, a lot. In which course? 240. Okay, I see. I'm not going to do this a lot then. But this is binary coded decimal. This is one example that I like. It's actually the Wikipedia example. But it's nice, right? And this kind of demonstrates the semantic level in a sense. So binary coded decimal, basically each digit is encoded with a fixed number of bits. And this also determines a lot of trade-offs, by the way. But if you look at this, each decimal digit in the clock is encoded with a fixed number of bits, in this case 4 bits. Right? And you can actually visualize it such that you can read a BCD clock. How many of you walk around with BCD clocks? You do? You have one?
Oh, well, I don't walk around with it.
Oh, you have one. That's good. And you can build one easily, right? Okay, but this, if you look at this, the semantic level of this is really close to a decimal, which is very much used in, maybe not the languages, but by people in this case. And this is a BCD clock, right? But this leads to other trade-offs. So there are BCD operations in x86, for example. They're used sometimes, but they're not the most common data types today. So x86 has binary coded decimal as a data type. Okay, so you can think of the closeness of the semantic level of the data type by just thinking, oh, okay, this clock can represent the decimal values that I have in my daily life almost, right? The semantic level of this data type is closer to your daily life, which means that there's not a huge semantic gap. Because by looking at this, well, you've got to be a computer geek, I guess, to read this. You have 1, 2, 1, 5, and 4, 5 here, right? By looking at the locations of the LEDs that are actually lit. Okay, that's fun. Okay, what other elements of ISA are there? Memory organization is also specified by the ISA. And there are many things related to it, and we'll talk about that, especially later in this course. Address space, for example, it determines how many uniquely identifiable locations are there in memory. That's part of the ISA. The programmer needs to know this. Addressability, how much data does each uniquely identifiable location store? That's part of the ISA. You could have ISAs that are byte addressable. Most ISAs, because characters are 8 bits, a lot of people decided byte addressability is a good idea. Because you usually operate at least on 8 bits. Not all ISAs were like that, actually. First alpha was word addressable. It's 32 bits. Basically, you cannot address a byte within 32 bits. If you would like to extract a byte, you need to do a lot of shifting and masking. Well, they figured out that was a bad idea. In a sense, this gives you the so if you have a 32-bit addressable machine, then you do not need to support byte operations, right? So it makes the ISA simpler, in a sense, makes the hardware designer's life simpler. Again, even this is an example of the trade-off between programmer and the microarchitect. If you do word addressability, it's simple for the hardware designer because you don't need to support byte operations. You just need to support word operations, and that's it. But it turns out programmers wanted byte operations because there were a lot of programmers who operated on images, for example, pixels. Well, alpha designers later said, okay, we're going to add the byte operations. Now you have byte operations as well as word operations. Harder for the microarchitect, slightly, but a great benefit for the programmer. 64-bit addressable, some supercomputers have this actually, because they operate on large data values. It's a specialized engine again, as an example. Bit addressable, at least, well, this one has been less common. You can address every single bit in memory. You can say, load this bit. A load operation specifies a bit, basically. That's nice, right? Well, one of the few machines that had this was Burroughs 1700. In fact, the reason it had this was because they wanted this machine to be a virtualized architecture. It could execute any ISA. And if you could address a bit, well, that's the smallest thing you can address, right, with any ISA. Which means that you can actually translate any instruction to any bit addressable instruction. This is a machine that's way ahead of its time, by the way. It's in the 1960s. It's pretty interesting to read, and I'll give you the reference for it. But there are reasons to have bit addressability also, because if you're going to operate on single bits, or if you're going to design a virtual machine that's really flexible, that may be a good idea. I'm not going to, well, this is not part of your homework, but this is something you can think about. Assume that you have only byte addressability. How do you add two 32-bit numbers? And assume that you have only 32-bit addressability, word addressability, which is the first alpha. How do you add two 8-bit numbers? This could be a good homework question, or maybe an exam question. You can think about it. There's also a big, related to memory organization, there's big endian versus little endian. Your most significant byte can be at the low or high byte. This is really a convention in a sense. And we'll get to that. You'll learn about it when we talk about MIPS. You guys know about big endian versus little endian architectures? Most of you probably do. Okay. Support for virtual memory, which we will cover a lot. That's also an element of the ISA. Does this machine support virtual memory? Right. Your answer could be no, because virtual memory adds its own overheads, as we will see. Okay. So if you want to dig deeper on what I discussed a little bit, you can look at this paper. It's a little bit difficult to read, but it's kind of a beautiful paper. And this book chapter talks about the Intel 432, which is an object-oriented architecture. Okay. There are many other choices. So let's talk about registers. Right. Again, an ISA specifies how many registers you have and the size of each register. Right. And it can have many different sizes also. x86, for example, evolved over time. It started with 8-bit registers, and then they added extended registers, 16-bit registers, and then they extend again, 32-bit registers. And now they have x86 64-bit registers. So it's kind of a mess, right? It's growing over time. But you can even make the choice of not having registers at all, right? So the answer of an ISA designer to how many registers could be 0. I don't want any registers. But why is having registers a good idea?
Accessing would be faster.
That's right.
You reuse
You reuse the
the data.
data. That's right. I like the reuse the data answer because that's really the concept, right? If you're reusing some value over and over and over, you may not want to go to memory and access it slower every time. So if you have, basically reuse means locality also. These are programs exhibit a characteristic called data locality, which hopefully you've seen in the past, right? In 213 at least. A recently produced or accessed value is likely to be used more than once. That's temporal locality, or reuse property. And storing that value in a register eliminates the need to go to memory over and over, right? Each time that value is needed. So having registers, assuming you have locality, then having registers is probably a good idea. Now the compiler, let's say, can identify what is reused and allocate those values into registers. You load from memory and put it into the registers. Programmer can do that also. So that brings us to programmer visible architectural state. So architectural state is the state that's visible to the programmer. It's definitely the memory locations, the program counter, assuming a von Neumann machine, and registers also. And registers could be general purpose versus special purpose. In a sense, these could be distinct from the memory locations, right? You could actually, they don't need to be caching, if you will, the memory locations that you use a lot. You could actually start with a 0 register and produce values over there. It's kind of specialized memory that's accessible by the programmer with a different means. We'll see, we'll add some other things over here, like the cache, which is programmer invisible, in a sense that its purpose is different from the registers. Right? Some purpose is similar, some purpose is different. Okay, basically instructions and programs specify how to transform the values of this programmer visible state. You can think of an instruction as taking this architectural state and transforming to some other state. And how that's done is specified by the definition or description of the instruction in the ISA. And we'll get to this when we start talking about microarchitecture, because there are many ways in which you can do this state transformation. In the end, the machine you're building is really a finite state machine. It's a sequential finite state machine, right? If you look at it, this is your beginning state, and you execute an instruction that takes you to some other state. Okay. So aside from the programmer visible state, we'll have programmer invisible state, microarchitectural state, and programmer cannot access this directly. Cache state and pipeline registers are examples. And we'll get to this later. Let me talk a little bit about the evolution of the register architecture, and then we'll take a break. So we'll talk about the accumulator machine, right? In this case, you just have one accumulator. Even before, that's the stack machine. Stack machine doesn't even have an accumulator. Accumulator is a specialized location, just one register. Very specialized register. You just accumulate on top of it. And then later, people started adding address registers so that they could support access to memory, indirect access to memory. Basically, you can store an address here, and then you can manipulate that address and then access memory. Initially, these address registers were actually a special purpose. You could only use this for accessing memory. Eventually, people started using those for the arithmetic operations also. So they became general purpose registers. So today, most machines have general purpose registers. All registers are good for all purposes, at least all general purpose registers, right? You don't have different address registers versus data registers. Right? Well, you do have the program counter. That's kind of special, right? Program counter is really a register, but it's really a special register. Stack pointer depends on which machine you're talking about. x86, stack pointer is still a general purpose register. It's called the ESP or SP, stack pointer, but you don't have to use that as a stack pointer. It's just a convention that people use it as a stack pointer, but it's really not specialized. Well, I guess it's specialized for some operations that operate on the stack pointer, right? But as long as you don't use those operations.
Then in other ones there, like in ARM, it's a separate one.
That's right. There could be architectures where it's separate. You're right. That's right. That's right. Link register is an example. You're right. Good. You guys are thinking. I like that. Okay, let me actually cover. Okay. Basically, general purpose register size also grew from few registers. So x86 originally had 8 registers. And people found that this is really small. And we'll talk about the size of the register file. This is, again, another thing that's specified by the ISA that affects lots of trade-offs, right? If you have few registers, now you have the ability to operate on few values at a given time. What if the program is such that it needs to operate on 9 values at a given time instead of 8? Well, you're trashing the register file, right? The programmer or the compiler somehow needs to save the register and restore the registers to be able to operate on 9 values instead of 8. So architects grew the size of the register file to 32, and this is common for a lot of RISC architectures, and to 128 in Intel IA64. And there are trade-offs in growing the size of the register file also, right? So let me finish this also, and then we'll take a break. So there are instruction classes. These are also specified by the ISA. This is really quick. Operate instructions, basically these process data, arithmetic and logical operations, right? What they do is they fetch operands, compute the result, and store the result. And they have implicit sequential control flow in a von Neumann machine. You always go to the next instruction. Right? Data movement instructions, they move data between memory, registers, I/O devices. Again, these have implicit sequential control flow. There are also control flow instructions that change the sequence of instructions that are executed in a von Neumann machine again. And we're going to cover a lot of these. And these also have different types. So if you look at MIPS, for example, control flow instructions are of J type. I guess data movement and operate instructions are kind of mixed. There's another element of the ISA, load store versus memory-to-memory architectures. Basically, do the operate instructions operate only on registers, or can they also operate on memory locations? Right? A load store architecture says operate instructions operate only on registers. A lot of the RISC ISAs actually make this trade-off. You have to move a value from memory to the register before you can do an operation, before you can do an add on it. Whereas memory-to-memory architecture, in such an architecture, operate instructions can operate on memory locations. This doesn't mean that they don't have registers. They still have registers. But you can also do direct operations in memory. You can do an add. You can increment a memory location, for example, without moving that memory location into a register. Right? So now you can think about the trade-offs, right? Well, this is definitely more complex now because you have more operations that can do operations on memory. But this could be more powerful, right? What if you're not going to reuse that value? What if all you're doing is incrementing 1 billion locations in memory, and you're never going to touch those locations? Why do you need to bring all of those into registers? Right? You can just keep them in memory and increment stuff while keeping values that you're going to reuse later in the registers. You don't need to clobber the register file. So there are benefits to the memory-to-memory architecture. But it comes at the cost of complexity. That's why a lot of the CISC ISAs have it, whereas the RISC ISAs don't have memory-to-memory operations. Addressing modes, I promised that we would get to it. We'll get to it even more later. But this is just to give you an example. Addressing mode, again, specifies how to obtain the operands. And there could be many possible addressing modes. Absolute says use the immediate value as the address. Basically, this immediate value serves as your address to load from. Register indirect, use the general purpose register. And then you can add some offset to that register value to compute your address, right? This is base plus offset addressing, if you will. Indexed, you can add 2 registers to form your address, base plus some index. And these could be valuable for some reasons, right? And I'll give you some of those reasons. Memory indirect, basically you take the value in the register, use that as an address, go to memory, and use that as an address. So you do double accesses to memory, instead of one access. Auto increment decrement, basically you use the register as the address, but after you do the access, you increment or decrement the register. It's called auto increment or auto decrement addressing. Can you guess why this could be useful? Yeah, if you're traversing an array, for example, if you're loading one location and then the next location you're going to load is the next location in the array, next address, you just automatically, the load instruction automatically increments the general purpose register that's used as the index into the array. Right? This is nice because you don't need to now have another operation that adds 1 to the register that's your address. So again, this is a design choice that the architect makes. It reduces your code size, right? Well, what is it? The downside is now it increases the complexity of your load instruction, right? Because you need to do an add in addition to doing the load. So all of these different addressing modes are another example of the programmer microarchitect trade-off. If you have more addressing modes, you can do better mapping of the high-level constructs to the machine. And I'll give you more examples of this in the next lecture. I wish it was this lecture, but it's going to be next lecture, given the time. Some accesses are better expressed with a different mode. As a result, you get reduced number of instructions and reduced code size. For example, the auto increment mode is one very simple example, right? If the address is automatically incremented, you don't need an additional instruction, which reduces the number of instructions as well as your code size. If you have this memory indirect addressing mode, you can store a pointer in memory, and you can use that as the address of another location, right? That enables pointer chasing if you have linked data structures, for example, if you want to do indirect accessing. Sparse matrix accesses, so you can have a sparse matrix that's huge, but a lot of the values are 0. You can have another array that basically has pointers to non-zero values, right? Now, if you have a memory indirect instruction, you can easily use that array with a single load to index into that sparse matrix. That's much larger, right? Basically, you can support complicated data structures as you increase the number of addressing modes that you support. Support meaning basically the implementation becomes easier. You can implement the high-level language with a reduced number of instructions and reduced code size. The disadvantage, again, remember, this is the programmer microarchitect trade-off. You're making the programmer life easier, or compiler writer's life easier, but you're making you're causing more work for the microarchitect. I say more work for the compiler also. That's actually more work for the compiler too, because now the compiler needs to figure out what is a good mapping, right?
It's
That's right. What is the best option to use? So even though I say programmer versus microarchitect trade-off, there's some gray area in the compiler here. Because you're giving lots of options to the compiler now. That may not always be a good thing for the complexity of a compiler. If you give one option to the compiler, that's really easy, right? The compiler designer just compiles to that. And you don't have any other option. But if you have 10 different addressing modes, or 50 different addressing modes, let's say, well, now the compiler becomes more complex, right? You have a lot of special cases. But in the end, it's good for the programmer. So not all programmers are equal in that sense, right? Maybe supporting more addressing modes is good for programmers that are really at the high level, but that may be bad for low-level programmers who really need to support those addressing modes also. But they're definitely more work for the microarchitect, because the microarchitect needs to support them in hardware. Another example of ISA property, one ISA property is orthogonality. An orthogonal ISA, this is the definition, is one where all addressing modes can be used with all instruction types. Why is this good? Well, this is good for the compiler, actually. Now, compiler is flexible. They don't need to have special case different addressing modes. VAX was an example of this. And I'll give you some examples of its addressing modes later in the later lecture. But it had 13 different addressing modes. It's kind of crazy, 13. x86 doesn't have 13. It had more than 300 opcodes, which is also a lot. And it had integer and FP formats. So now you could combine, mix and match all of those. Right? In a sense, you could have 300 times 13 combinations of addressing modes and instructions. So it was very flexible. Well, I guess, who is this good for? Who is this bad for? It's good for someone. It's bad for definitely someone else. It's bad for the microarchitect. You can actually guess that, right? Because now you need to support a lot of things. It's good for the compiler designer, again, because they don't need to think. They can use any addressing mode and get working programs. That doesn't mean that they're the best programs for this architecture, right? So one example, is the LC3B ISA orthogonal? Well, you don't know the LC3B ISA. I'll give you the answer soon. But again, this means that all addressing modes are supported by all opcodes, right? Any instruction type can support any addressing mode. Well, it's not in this case. If you look at this, if you just look at this, not all instructions have the immediate addressing mode, for example, right? Or not all instructions have the PC plus offset addressing mode. As a result, it's not orthogonal. These are the addressing modes of add, and I'm going to go through these relatively quickly. You can have two addressing modes, right? You can have register addressing mode. The source operands are in registers, or you can have immediate addressing mode. One of the source operands can be immediate value. These are the addressing modes of jump to subroutine. Basically, jump to subroutine determines its address. Basically, this is similar to a jump and link, if you will. But the destination, the program counter, is either set to a register, which means that it uses the register addressing mode, or it could be this immediate, right, which is PC plus offset. But immediate is not just immediate. You add the program counter to it. So this is called PC relative addressing. Right? Well, I don't think I'm going to switch to it, but it's PC relative addressing. By the way, this is the advantage of a whiteboard. You can switch to it much faster than you can switch to this thing over here. I guess if I kept it turned on, I could have switched to it. But this is PC relative addressing. And add definitely doesn't have the PC relative addressing, right? You cannot specify a source operand based on how far away it is from the program counter, current program counter. PC relative addressing is good for procedure calls because now you can place the procedures close and actually jump to PC plus some value. Right? So definitely LC3B is not orthogonal. Okay. Any questions on this? Okay. I guess I can talk a lot more about the JSR instruction, but I'll leave it up to you. So the other elements of the ISA, how to interface with the I/O devices. Even this is a choice in the ISA. You can use memory mapped I/O. Basically, a region of memory is mapped to I/O devices. Whenever you're accessing them, you're really accessing the I/O devices, load, store. And this mapping is formed at the beginning when the system is set up. Yes, or you can have special I/O instructions. For example, x86 has in and out instructions that deal with the ports of the chip. You can specify which port of the chip you're getting out of. x86 also has memory mapped I/O, by the way. That's what makes it complex. You can do many things in different ways. You can do the same thing in many, many different ways. So there are trade-offs related to this also. So everything has a trade-off. Which one is more general purpose in this case? Memory mapped I/O, you say. Yeah, that's right. Well, it's kind of explicit, right? I already said special I/O instructions, which means that they're special purpose. Right? Whereas memory mapped I/O, any kind of device can be accessed as long as you map it to a memory region, right? You can load from the keyboard. You can store to the monitor. There are many other elements of the ISA, privilege modes, what kind of privilege modes you can have, who can execute what instructions, at what privilege level, what can you do. These are specified by the ISA. I'm not going to cover that right now. Exception and interrupt handling, for which we will have a lecture. What procedure is followed when something goes wrong with an instruction? You're executing a divide operation, and the second operand happens to be 0. You get a divide by 0 exception, right? What happens after that? That's specified by the ISA. What procedure is followed when an external device requests the processor? That's the exception, right? That's the interrupt. And we'll distinguish between interrupts and exceptions. Interrupts are external to the executing program. Exceptions are internal to the executing program. Vectored versus non-vectored interrupts. Again, we're going to talk about this also. Well, I guess I'll give you an example here. Do you guys know what is vectored versus non-vectored interrupts? Anybody? No? When an interrupt happens, that's right. So actually, that's right. So with a vectored interrupt, when an interrupt happens, when a device interrupts a processor, it also writes, or somebody writes which device is interrupting the processor in a register. This is called vectored interrupt. And using this information, you can determine where to jump to service that interrupt easily, to the interrupt service routine. Non-vectored means this information is not available. The only thing you know is somebody is interrupting the processor. Well, the trade-off over here, early MIPS, for example, because they wanted things to be simple, they said, we don't want vectored interrupts. We want to be simple, so whenever an interrupt happens, the processor needs to somehow figure out who's interrupting. So what the processor did was, it went through all of its I/O devices and said, did you interrupt me? Did you interrupt me? Did you interrupt me? Did you interrupt me? Well, bad idea, right? In a sense. It may be a good idea as long as if you cannot store this address or store which device is interrupting you. But now MIPS actually has vectored interrupts. So that's a trade-off also. Virtual memory, we've talked about this. Each program has the illusion of the entire memory space, which is greater than physical memory. Is this supported or not supported? How is it done? We'll cover several lectures on this. That's part of the ISA. Access protection, again, if you don't have the privilege level to access a location, what happens after that? Okay, but let's talk about instruction complexity a little bit, and hopefully we'll conclude after 20 or so slides, because this is an important topic. Because it's not as simple as it sounds. I'm going to introduce something that changes all of the trade-offs that you can have at the ISA level. Can anybody guess what that is? How many of you are looking into the future that far enough? Or have had enough coffee to generate a random guess? Okay. Does the LC3B ISA contain complex instructions? And the answer is no. It doesn't contain complex instructions because, well, anyway, take it. You're going to see the instructions. They're really simple. How complex can an instruction be? These are actually interesting questions. Complex instruction, what is a complex instruction, first of all? An instruction does a lot of work. That's my definition of it. That's perhaps the best definition. Because it's hard to quantify what is complex, right? For example, many operations. On the other hand, simple instruction does small amount of work. It's really a primitive using which complex instructions can be built. So a complex instruction, I don't think anybody is going to argue that inserting in a doubly linked list is not a complex instruction. It's a complex instruction, right? It does a lot of things. Compute FFT. Now that's a little bit complex too, right? Add to or average some number of pixels. That's a complex also. String copy. Simple instruction, well, think simple. Add, XOR, multiply. Even multiply was complex for early RISC designers. MIPS didn't have a multiply instruction, for example, to begin with. And later, people complained and they said, oh, we have lots of multiplies. We don't want to translate it to a loop that does adds and shifts. So they added the multiply instruction. Right? So even multiply is more complex than add or XOR. You have a question?
Yeah. What would you consider traps? Like, isn't that like a composition of a lot of pushes and all?
Well, a trap is a little bit different. That's more complex than add, but it's something that you may need to support system level operations, right? In a sense, privilege level. So one thing that a trap usually does is it changes the privilege levels. Right. So that's something that you really need to do to build a good operating system around the system.
So would that still be simple? Or?
I would say it's simple, yes. Because it's something that you really need to do a critical task, and there's no other way you're going to do it. Maybe you can simplify it also. Maybe you can have instructions that just change the privilege level. But you could consider that a trap also, right? So even traps can have different levels of complexity. You can say either this instruction just changed the privilege level, or you could say this instruction changes the privilege level and also does a bunch of things. Usually to be secure, you need to do all of those bunch of things also. Otherwise, you can change the privilege level and hack the machine, right? By loading some things. Anyway, we're not going to go into that. There are security aspects related to how you design the traps also. OK, so what are the advantages and disadvantages of complex instructions? What is the advantage? What is the biggest advantage of having a complex instruction? Smaller code, yes. The answer encoding, right? You get, as a result, actually, smaller code is one benefit of the answer encoding. There are many other benefits. Better memory utilization, I guess that comes from the smaller code. You can save off-chip bandwidth when loading instructions. You can get better cache hit rate because your pack instructions much better into the memory space. You don't need as much memory, perhaps, right? And simpler compiler. You don't need to optimize small instructions as much because you don't have the freedom to optimize in a sense, right? You can compile to these complex instructions. But there are disadvantages also. Now you have larger chunks of work, right? And the compiler has less opportunity to optimize because it's limited in how fine-grained it can reorder the instructions. If you use an instruction that inserts into a doubly linked list that's implemented by hardware, compiler cannot reorder individual operations, right? And also more complex hardware, right? Because now you have complex instructions, and the hardware needs to translate those to the control signals, and it needs to optimize them. So you can have an insert into a doubly linked list, but it can run really slow, right? If you don't optimize them. So the optimization needs to be done by the hardware. So this leads us to the semantic gap again. Basically, this is a trade-off. The complexity of the instructions or complexity of the operations in the ISA is determined by the choice of where do you place the ISA. You could choose to place it closer to the high-level language. As a result, you'll have small semantic gap and complex instructions. This decided to die on me. OK. No. It's better. Oh. Let me draw this again. So you have, as an architect or as an ISA architect, you have a choice. You have this high-level language that you're building your machines for, and then you've got to execute them using some control signals in the hardware. And you have a choice of where to place your ISA. It's better. Well, you can say my ISA is closer to the high-level language. So I'm going to have instructions complex that can implement operations that are specified by the high-level language, linked list operations, for example. Or you can say my ISA is over here. And the semantic gap is how far is your ISA from the high-level language. Can you guys see this? OK, good. That doesn't mean that you're able to read it because my handwriting is terrible. But hopefully you're following my audio at the same time as I write. So semantic gap is how far away your ISA is from the high-level language. If it's closer to the control signals, you have a large semantic gap, but simple instructions. Well, it's not exactly perfect, actually. If you're too close to the control signals, if you expose all of the control signals to the ISA, now your complexity also increases, right? So take this with a grain of salt. The curve is probably, your complexity is high at the top level, but then your complexity also increases very close to the control signals. But RISC versus CISC machines, RISC is reduced instruction set computer. CISC stands for complex instruction set computer. They basically differ in terms of where they place the ISA. For example, you can think of quicksort instructions, right? VAX index instruction. This was a real instruction. It did array access, I believe you could do 5-dimensional array access with bounds checking at the same time with a single instruction. It's kind of beautiful in a sense. You could support languages that support bounds checking in their arrays, right? Like Java, easily, right? And you could do multiple dimensional array accesses. But it's complex. So now you're closer. With the VAX index instruction, you're really closer to the high-level language over here. Whereas all you had was add, multiply, then you're much closer to the control signals. And the compiler needs to compile that indexing and bounds checking all the way into those smaller, simpler instructions. So there are many trade-offs, again, with the semantic gap. Do you have a simple compiler, complex hardware, versus complex compiler, simple hardware? Right. If the instructions, if your ISA is here, if you have a large semantic gap, your hardware can be much simpler, right? Because it's dealing with simple instructions. But now your compiler needs to be more complex, at least to get a good level of performance. Let's see. But one thing can change the trade-off. This was the word I was looking for. And we'll get to this. Translation or indirection can change the trade-off. And we'll finish this lecture with a more detailed investigation of this. Can anybody guess what that is?
You compile once more to smaller.
That's right, exactly. I wouldn't call that compile, but you translate it. Basically, you have another level. Well, I don't see it here. I need another. The purple pen comes to the rescue. So you have another level. You translate this to something else in between. And we'll see that. A lot of machines actually today do that. The other trade-off is burden of backward compatibility. So let's say you've added a complex instruction that was good for one high-level language. What if the future high-level languages don't use it? Now you need to support those complex instructions because people may still be using those complex instructions, but most of the languages are not using it in the future, right? So this is affected by where you place the ISA. If all you had was add, multiply, XOR, they're very primitive, right? You can bet going into the future that people will still be doing adds, XORs, multiplies. Right? Whereas it may be difficult to guarantee that people will be doing quicksort all the time. Right? There are trade-offs on performance and energy consumption. Who has the optimization opportunity? Is it the compiler doing the optimization? Is it the hardware? Who puts more effort into optimization? One argument when reduced instruction set computers were developed in the 1970s was, at that time, people were designing instruction sets that were with complex instructions. So semantic gap was very low. And one argument was VAX was one of the most popular ISAs at the time. And people who were proponents of reduced instruction sets examined the VAX programs, and they said, this VAX index instruction runs like a dog. So they took a program, VAX program, and they compiled into VAX index instructions, and they also compiled into primitive operations in VAX, and they said, if you use the VAX index instruction, the program runs, in fact, much, much slower, orders of magnitude slower. So complex instructions are a bad idea. Do you buy that? No. Some of you don't. Yes, exactly. Well, if it's implemented slowly, then it's probably a bad idea. Right? So it turns out later other people also examined the situation. They said most of the programs do not even use the VAX index instruction. So VAX designers made the choice to not optimize it as much. So it's kind of interesting, right? You're affecting a lot of things here. Well, if you haven't optimized that much, maybe it's not an interesting instruction to have in the ISA anyway, right? So, but this points out to a key trade-off. If your semantic gap is low, meaning you have complex instructions, the hardware needs to put more effort into optimization. Otherwise, those complex instructions are useless, right? You might as well implement everything with simple instructions. And also, there's trade-offs on instruction size, code size, energy consumption. So instruction complexity affects a lot of these. Let me give you some other examples of these complex instructions. x86, actually, you'll do this in your homework. You have a small semantic gap in x86, smaller than many ISAs. You have string operations. An instruction basically operates on a string. You can move one string of arbitrary length to another location. You can compare two strings. And this is enabled by a very powerful primitive that x86 designers added to the ISA. And that's called the prefix. And in particular, the repeat prefix. x86 has multiple prefixes. One of them is the repeat. Basically, before the opcode, you can add a prefix that says repeat. Basically, some number of bits that are interpreted as a prefix that qualify what happens to the instruction. And repeat happens to say, repeat this instruction until something happens, until the count register becomes 0. It's kind of powerful, right? Now you can implement loops with a single instruction by just adding this prefix. That's exactly how the string operations are implemented. Basically, you have a move s instruction, move string, and then you can repeat it over time. And this could be specified by only 2 bytes. You can move arbitrarily long strings, or you can copy arbitrarily long strings using just 2 bytes. And that's the opcode. A4 is the opcode of move s, and F2 is the specifier of the repeat prefix. It's kind of beautiful, right? Imagine moving a billion locations just with 2 bytes instruction. Because we have an implicit source and destination registers that are pointing to 2 strings, source and destination, ESI, EDI, that S and D actually stand for source and destination. Actually, source index and destination index. And then E means extended. And then you have an implicit count register, ECX, count register. Specifies how long the string is. And this is a specification in x86 manual, at least in an older one. So it's complex, as you see. Basically, you have while count register is not 0, you service pending interrupts first, and then execute the associated instruction, which is defined that way. You decrement the count register. If count register is 0, then exit. Otherwise, you do some stuff, right? So with one instruction, you can do all of this. It's very powerful. This is what a complex instruction is. And your task in homework 1 will be to do it in MIPS. You'll see how many instructions it takes in MIPS. And hopefully you'll optimize it. It's fun, right? So it's beautiful. Now you can actually, now this makes the compiler writer's life easier, right? If you have string copy, well, this is string move, but you can do string copy also. Well, I guess string copy and string move are the same, right? I was trying to say something else, but that's okay. Yeah, this is basically string copy, right? Implemented in hardware with just 2 bytes. There are other examples. VAX, this is another handbook that I would recommend you read. It's actually a lot of fun to look at this. VAX has a lot of examples. Find first. It finds the first set bit in a field. Right? Save context, load context. This is good for context switching. And we talked about the instructions that operate on doubly linked lists and array accesses. It also has string operations. It has an instruction for cyclic redundancy check. So it could be useful for some operations. It has edit PC instructions. These implement editing functions to display fixed format output. It's kind of interesting, right? That they encoded. They actually designed instructions for this purpose, to interface with the monitor. Now, these may not be very forward-looking, right? Going forward, maybe your output is different, right? Now, they added some flexibility to the format, but it may not be very useful today. So this handbook is very humbling and instructive. I'd recommend that you take a look at it. It's linked from our website. Right, Kevin? It should be. If not, it should be. OK. So small versus large semantic gap. We're going to spend the next 10 minutes on this probably. Complex instruction set computer, you have complex instructions. Initially, this was motivated by not good enough code generation. Well, why did people start with complex instructions? Because the compilers were not good, actually. Compiler technology didn't develop well. As a result, it was easier to have complex instructions than say, OK, I'm going to convert the high-level language with a very simple compiler. But later, people decided, oh, maybe it's time to look at reduced instructions, have simple instructions. This is John Koch. It's another Turing Award winner. He's the designer of the early RISCs. IBM 801 was an example. His goal was to enable better compiler control and better optimization of programs because these complex instructions were not necessarily being optimized well in the hardware, according to him. And we'll get to this again, but there are many motivations for having simple instructions. First of all, hardware can be simple, right? It could be low cost, higher frequency. The compiler can optimize the code better now because it can move these operations. And these big instructions, big chunks of instructions were causing a lot of stalls. What does that mean? Let's say you have a string move operation. That string move operation, if it kept accessing memory, it would keep stalling. And there was no way to optimize these little operations that string move really does inside. For example, it increments the count register, right? There was no way to optimize that if you had a single instruction to deal with, right? Yes?
Also, it can't take an interrupt till then, right?
Well, that's right, but if you look at the x86 specification, you can take an interrupt in the middle of at the beginning of every iteration.
Oh, even with repeated.
That's right. That's right. OK. So an aside, if you would like to learn about the historical perspective on RISC development at IBM, this is really a short, nice link. It's from the IBM perspective, so you'll get some IBM party line in there, but it's good to look at. So very large semantic gap. Each instruction specifies a complete set of control signals in the machine. That's the, in a sense, lowest you can go in terms of where you place the ISA. Your ISA could be the control signals, right? This gives a lot of opportunity for the compiler to optimize the program, right? Assuming it has that information. But then it becomes really complex. And this was the concept of open microcode. The person I showed you earlier, John Koch, he had this idea in the early 1970s, which eventually led to the concept of RISC. And it gave way to optimizing compilers. Basically, he wanted to design a compiler that optimized each of the control signals in the machine. Now, that's very tough to do, right? Because you need to expose a very different interface. You need to expose every single control signal. And it becomes very inflexible in the end. But this is what the dreamers enable going into the future. He dreamed that you could modify the control, you could optimize the control signals. And eventually, he settled on the low-level primitive instructions. Right? On the other hand, you could have very small semantic gap. ISA can be almost the same as high-level language. Java machines. People decided to build Java machines, for example. That's an example. Lisp machines. Do you guys program in Lisp? No? How about Prolog? These are usually used for artificial intelligence, if you will. Okay, maybe we'll talk about that. But basically, these were languages that were normally slow. But if you actually implement the operations at if you have a small semantic gap, you could implement a lot of things in hardware, so you could accelerate these languages. So there were a lot of machines that were built, Lisp machines, that had very small semantic gap. And I'm not going to talk about some of the other ones. But I'll talk a little bit about ISA evolution. ISAs have evolved to reflect and satisfy the concerns of the day. So examples, if you have limited on-chip and off-chip memory size, maybe you want complex instructions, right? And that was one of the motivators. If you have limited compiler optimization technology, then again, you have complex instructions because compiler can easily compile to them. If you have limited memory bandwidth, again, maybe complex instructions is a good idea. If you have a need for specialization in important applications, maybe you add more instructions, like MMX, as we've discussed. I think I'll very briefly discuss translation and finish it afterwards. If you use translation, you can actually change a lot of these trade-offs. You can basically enable underlying implementations to be similar regardless of the ISA. Can anybody guess why? Well, you're literally adding an indirection level. One can basically translate from one ISA to another ISA to change the semantic gap trade-offs. And what do I mean by one ISA to another ISA? ISA, let's call it the virtual ISA. This is the hardware-software interface. This is what the programmer, or most programmers, see. And then there's something in between. Well, maybe I'll draw this figure again. You start with a high-level language, and you need to go into control signals. And assume that what I wrote here is control signals. You have an ISA that's complex with small semantic gap. I'll call this a virtual ISA. Most programmers write to this. That's what they see. But then underneath, you can have an implementation ISA. And you can have something in between, let's call this the translation engine, that just does translation. It translates these complex operations into simple operation. You could think of this as a compiler, right? Another compiler that sits in between. And now you can change the trade-offs between the hardware and the software. This is the hardware-software interface that the programmer sees. And you can think of this as the translation and execution interface, right? This is where translation stops and you start executing in hardware. So this may be your real processor, if you will. And here, in between, you could have this translation engine can be in software or hardware. Right? Now, what is the implication of this? Oh, I guess you can still see it. What is the implication of this? The implication is that you can have a really complex ISA that's exposed to the programming language, programmers, and you can get the benefits of those complex instructions while keeping the processor simple. Because now your processor needs to execute stuff that is converted into this implementation ISA. And the implementation ISA can be really primitive operations, right? This could be reduced instructions or simple instructions, add, multiply, XOR. And that could be doubly linked list addition. And now somebody needs to do this translation, though. Now there's where the complexity comes in. Who does that translation? I'll take that later. Well, in most processors that you use today, it's the hardware that does that translation, actually. In Intel's and AMD's x86 implementations, x86 ISA, x86 instructions, which are complex instructions, they're translated into programmer invisible micro-operations that are simple in hardware. So if you look at an x86 processor, you have a hardware engine that does this translation. Hardware translator. It's nice, right? Did you guys know about this? But that's how they made the core of the processor simple. You have this hardware engine that does the translation, and the core of the processor is now simple. It kind of looks like actually a RISC processor. In fact, all of the high-performance processors today underneath look like RISC processors, except the ones that actually have a complex ISA do this translation. They have some additional hardware to do the translation. Well, you can think about doing this in software also. In Transmeta, how many of you know Transmeta? Oh, you guys are young. Transmeta was a company that wanted to compete with Intel in the late 1990s. And what they wanted to do was to implement this translation engine as software, purely. And they actually did. They called this the code morphing software. They could execute any x86 program, and a dynamic compiler, or dynamic binary translator, if you will, translated that x86 ISA program into an underlying implementation ISA, which was a VLIW ISA. And their goal was to have a really efficient processor that's both power efficient and higher performance. And that was their code morphing software. So think about the trade-offs. So I'll give you a couple of pictures, and then we'll finish. This is from the paper that actually talked about the Transmeta technology, the technology behind Crusoe processors. We should put this online on our on the course website. But if you look at a processor today, you don't need to understand everything over here. While you're decoding, and this is kind of a cartoonish picture, while you're decoding x86 instructions, you're also translating them into micro-operations. And later, what gets executed is really the micro-operations. The complex instructions do not get directly executed. They get translated into micro-operations. So what you're doing in homework 1, you're taking repeat MOVS and translating into MIPS instructions You can think about the hardware doing it dynamically. And in fact, in many x86 processors today, what the processors do is they take the complex instructions, they translate them, and they save them in translated form. So that the next time in hardware, next time you get to that instruction, you don't need to translate it again. You just take the micro operations and execute those micro operations, simple operations. This is called a decode cache, a decoded instruction cache. Well, this is the other way of designing the system. This is figure 5 in this paper. Basically, what transmitter looked like was it could execute x86 code, and in between there was a dynamic compiler, code morphing software, that compiled at runtime the code into a VLIW engine. So if you look at this interface, this is x86. This is the x86 ISA. But internally, the processor had another interface, which is a VLIW, internal ISA that was not exposed to anyone in the world, except for people who wrote this code morphing software, which was proprietary to them. Okay. I think you can think about the trade-offs related to this. This is a very powerful thing. And while you think about the trade-off, get ready for next week. So we'll see you next week.